When you type a prompt into a standard large language model, the system executes a single forward pass computation. Input goes in, and text comes out. Once that output generates, the system forgets the interaction entirely. It has no persistent memory across steps, and it cannot reach out into the physical or digital world to execute external actions. This restriction forces the human operator to act as the primary orchestrator. To accomplish a multi-step task, a human must manually copy, paste, and feed intermediate outputs back into the prompt box to guide the model forward. The core promise of an AI agent is removing the human from that orchestration layer. We are moving toward a system-orchestrated autonomous loop. True agentic behavior requires moving beyond predicting the next word. It requires engineering a dynamic, stateful cybernetic system around the model. Look at the left panel. Simple LLM prompting is a linear pipeline, a straight line from user input to the final output. On the right, the new architecture wraps the model inside a recurrent control cycle, continuously moving through discrete stages of thought, action, and observation. This loop does not spin indefinitely. It repeats autonomously until a specific, mathematically defined termination condition is met, triggering the final output. Look at the memory and state row. A chatbot is limited to a single context window. An agentic system maintains an evolving state, updating after every step. The control flow row shows we are replacing the single pass with a repeated loop governed by constraints. In this configuration, the large language model functions as a policy engine, one part of a larger software system, rather than the application itself. This diagram details the micromechanics of that central engine. This is the thought-action-observation cycle, commonly called the Tau loop. It begins with observation. Here, the system ingests the initial user input alongside specific signals and data pulled from the external environment. In the thought phase, the LLM processes those signals. It reasons about its progress toward the goal and proposes the logical next step. In a production codebase, this entire cycle is governed by a standard while loop. The system will continue running while its objective remains incomplete. Every revolution of this cycle serves a single engineering purpose: to update a central data structure known as the state object. The state object is the agent's living memory. It meticulously tracks the interaction history, the user's explicit constraints, and the intermediate results of any tools it has deployed. Agentic autonomy relies entirely on this mechanism. It is simply a software loop continuously updating its state vector until a programmed constraint tells it to stop. To construct that loop, developers utilize a specific software stack. This 3D diagram illustrates the 4 interacting layers of modern agent architecture. At the very top sits the interface layer. This component receives the user's initial goals and sets the operational constraints. Immediately below it is the planning layer. Acting as the system's prefrontal cortex, it algorithmically decomposes the broad user request into a precise sequence of subgoals before taking any action. The bottom 2 tiers, the React control loop and the tool orchestration layer, handle the actual execution of those subgoals.
We are locking out the execution engine entirely for the remainder of this section. We need to focus strictly on the cognitive preparation occurring in the top half of the stack. If the interface and planning layers fail to correctly structure the task, the bottom layers will simply execute bad decisions at high speed. The planning stack is the architecture's most critical point of failure. Planning, in an agentic context, is the explicit decomposition of a high-level goal into intermediate executable subgoals. System architects determine how an agent will plan using this 2x2 matrix, known as the planner's playbook. The decision rests on 2 axes: latency and cost on the vertical, and task complexity and global coordination on the horizontal. In the bottom left, reactive planning makes step-by-step decisions based solely on the current context, without outlining a long-term strategy. This yields low latency. However, without a forward-looking plan, the agent risks missing necessary dependencies or falling into an infinite loop, endlessly repeating the same actions. Contrast this with deliberative planning in the bottom right, where the agent explicitly constructs a complete multi-step plan before making a single API call.
Moving up, step-by-step planning utilizes chain-of-thought techniques to force the model to translate a broad goal into a strict, linear list of instructions. Finally, in the top right, hierarchical planning deploys a top-level orchestrator model that delegates individual phases to highly specialized subagents, maximizing task reliability. The engineering reality is stark. Moving to the top right of this matrix massively increases the reliability of your system, but it exponentially drives up API token costs and processing latency. Designing an agent requires accepting that perfect intelligence is a theoretical concept. Production systems are a pragmatic, constant balancing act between cognitive capability and the computing budget. Let's apply this theory to a concrete scenario: an agent tasked with booking a 2-day business trip from Delhi to Bangalore under a strict budget. First, the interface layer extracts the hard constraints, the user's airline loyalty, the exact dates, and the spending limit, and writes them directly into the state object. The planning layer takes over, decomposing the massive request into a clear hierarchical list. Gather flight options, locate hotels, verify corporate policy, propose the itinerary, and execute the booking. This structured plan is firmly injected into the state object's memory before the primary execution loop is ever allowed to begin. At this exact moment, the system is fully initialized. The agent has perceived its operational environment and constructed a robust plan. All of the cognitive heavy lifting is completely finished. But a perfect plan is useless without a reliable execution engine. How does the agent actually traverse its loop, negotiate with external APIs, and decide precisely when to act versus when to rethink its approach? Bridging the gap between a cognitive blueprint and real-world action without triggering a hallucination requires a specialized execution architecture, and that is exactly what we will build in Part 2.